Okay, in this video, we're going to be graphing logarithmic functions. Now, first off, let's talk about what the parent function here would look like. Parent function would be y equals the log of x. A logarithmic function, and we've already talked about this, is the inverse of an exponential function. And as a result, it says using your graphing calculator, let's go ahead and sketch these. Y equals the log of x. Now, before I do that, let me graph y equals 10 to the x power, because I can do 10 to the 0, 10 to the first, 10 to the second a whole lot easier than I can do these logarithms. And we know that that's an example of exponential growth that looks something like that. Now, since these are inverses of each other, we know that they're going to be mirror images across the line y equals x. So there's what log base 10 of x looks like, and you can see that they are mirror images. Now it says here, kind of a falsehood. It says because you can only graph base 10 graph or logs on your calculator, you will need to use the inverse exponential function, then invert. Now we could graph other ones by using our change of base formula, but this does give us a very helpful way of graphing these. And let's show you that way on this first one. Instead of graphing, because it says graph each function, identify the key characteristics. Instead of graphing y equals log base 2 of x, sometimes it's easier to do this. Sometimes it's easier to actually find the inverse of this, which would be x equals log base 2 of y. We changed our forms there, and then just solve this thing for y. That would be 2 to the x power is equal to y, and graphing that instead, because think about how easy it is to plug values in to this, because we have before. We graphed that earlier in the chapter to where when you plug in let's do -2, -1, 0, 1, and 2. 2 to the -2 power is 1/4. 2 to the -1 was 1/2. 2 to the 0, 2 to the first, 2 to the second. And that was your values. But since we're instead wanting to graph log base 2 of x, that is simply the inverse of this function that we just plugged everything into. So how do we find those values? Well, we understand that inverses are simply switching x's and y's. So we use this to find our t-table, and now we can simply switch our x values with our y values, and we have the points to plot now for log base 2 of x. So there's all the points. Now let's plot them and see what it looks like. And there you see the graph of log base 2 of x. And again, the process: find the inverse, find all the x and y values of the inverse, and then simply switch the x and y values, and that's going to be the x and y values of the original function. So here you see the logarithmic graph. The domain, here you can only find the log values from 0 to infinity. Notice that you have that horizontal or vertical asymptote line on your y-axis. Your range there, however, goes down forever and up forever. So it would be negative infinity up to positive infinity. In behavior, as you travel to the right on your graph does go to, your y value does go to infinity, and you can see it going there. And then as x goes to 0, notice that you're approaching 0 here, and your graph shoots down to negative infinity. Your x-intercepts, you have an x-intercept here at 1, 0. Whoops. And you think about it, why do I have that x-intercept? Well, because you had a y-intercept at 0, 1 with y equals 2 to the x power. And again, your asymptote line here would be x equals 0, that vertical asymptote. Next one, instead of graphing y equals log base 1/3 of x, you can reciprocate that and graph instead x equals log base 1/3 of y. Change that to exponential form, which would be 1/3 raised to the x power is equal to y. And let's again make our t-table for that instead, because it's so much easier. So x and y, we can plug in the same -2, -1, 0, 1, and 2. Any fraction raised to a negative exponent flips the fraction, so that would be 3 to the positive 2, 3 to the positive 1. 1/3 to the 0 is 1, 1/3 to the first is 1/3, and 1/3 to the second is 1/9. Let's plot those points and look at, well, actually, let's not plot those points, because that's the points for y equals 1/3 to the x, we're wanting to graph its inverse. So therefore, let's reciprocate our points. Let's flip them over. 3, -1, 1, 0, 1/3, and 1, and 1/9, and 2. And let's plot those points instead. And here we see a look at that graph. My domain, again, notice that I can't take the log of anything 0 and down, so therefore my domain is from 0 to infinity, not including 0. My range is from negative up to positive infinity, up and down forever. As we go to the right, my graph decreases. So that would be as I go to the right, my graph decreases. As I approach 0, my graph increases. So they flip-flop those on me. My x-intercept is at 1, 0. And my asymptote line, again, is the y-axis, x equals 0. Next graph. And again, you could plug in points if you'd like to and graph this the other way, but it actually gives us practice finding inverses as well. So what I'm going to do is find the inverse, which would be log base 4 of y minus 1. I'm going to solve that by doing 4 to the x power, just writing it in exponential form and moving that 1 over, and you would get y equals 4 to the x power plus 1. So I'm going to graph this using a t-table. I'm going to simply flip-flop my x's and y's, and that's going to tell me my values for my graph that I'm trying to graph. So I'm going to plug in the same values, -2, -1, 0, 1, and 2. When I plug in -2, 4 to the -2, that's 1/16. So when you add 1 to it, I found a common denominator that's 17/16. Plug in -1, bring it to the bottom, that's 1/4 plus 1, that'd be 5/4 after you find a common denominator. Now these are easier to plug in. 4 to the 0 is 1 plus 1 is 2. 4 to the first is 4 plus 1 is 5. 4 to the second is 16 plus 1 is 17. Now let's plot these points and see what our graph looks. Well, again, I nearly forgot again. Make sure that's the graph of 4 to the x plus 1. To find the graph that you're looking for, let's reciprocate those. 17/16, -2, 5/4, -1, 2, 0, 5, 1, and 17, 2. And here's what your graph will look like. And there is your graph. Notice the transformation where my graph got shifted to the right one. That was because of the y minus 1 inside. However, my domain, that did affect my domain because my asymptote line actually moved over to x equals +1. So therefore, my domain here is going to be 1 to infinity. And again, a reason for that, you can do it like this. The stuff that you're taking the logarithm of, x minus 1 has to be bigger than 0. You cannot take the log of a negative. You cannot take the log of 0. Once you solve that by moving the 1 over, it tells you that your x values have to be bigger than 1. So therefore, that's how I get the 1 to infinity, or by looking at my graph. My range goes from negative to positive infinity. When does my graph go to infinity? That's as I travel to the right, my graph goes up. So that as x goes to infinity, my y goes to infinity. As x approaches this value of 1, my y value goes to negative infinity. I do have an x-intercept now at 2, 0. Next graph. Switch your x's and y's if you would like to, or again, you can plug this into your calculator, this log base 3 of x. If you'd rather just do a t-table for this, you could type in as the log of x divided by the log of 3 using your change of base formula. It's just, to me, it's much easier to plug stuff into an exponential function than it is into a logarithmic function. So here's my function. That's the inverse of my function. Now let's move the 2 over. That'd be x plus 2 equals log base 3 of y. And the reason I did that first on this one is because this -2 is not attached to the x. You can actually put that x in parentheses. It would have to have parentheses around all of it to imply that that -2 is included. But then you just change forms. That'd be 3 to the x plus 2 power is equal to y. Now let's do a t-table for those values. I'm going to plug in the exact same x values. And I actually had to, there they are, but I actually had to add a couple more x values in because of the way that this got shifted, so I can get some fractional answers. When I reciprocate that to find the x and y values that I need to be graphing, here's what I get. And then let's go ahead and plot those values and we'll see what our logarithm function looks like. Okay, now let's go ahead and fill out the attributes of my function. Notice that I do have an asymptote line. I want to do it first at x equals 0. And again, the reason for that is you can look back at your original. You cannot take the log of 0. You cannot take the log of a negative. So since you have log base 3 of x, 0 and negatives are off limits. So therefore, your domain would be, therefore, starting at 0, the asymptote line, and going to infinity. Your range goes down and up forever. Your function goes to positive infinity as you go to the right, and your function shoots down to negative infinity as you approach 0. You have a y-intercept right here at 9, 0. Next function. Okay, number 5, here's my function, and again, let's go ahead and find our inverse and graph it instead. So it's log base 1/2 of y plus 9 plus 4. Move the plus 4 over by subtracting 4. That'll be x minus 4 equals log base 1/2. That should be a base, so let's write it a little bit further down, of y plus 9. Change forms, that would be 1/2 raised to the x minus 4 power, and that's the whole 1/2. So I'm going to put them both in parentheses, equals y plus 9. And if you move that over a little bit, you can go ahead and to get rid of plus 9, we can just subtract 9 right here. So that's what we're going to graph right there. Let's go ahead and make us a little t-table. And so that I can get some negative and positive exponents in here. If you'll plug in, let me think for a second, maybe 2, 3, 4, 5, and 6. Notice that 2 minus 4 gives you a negative 2, 3 minus 4 is negative 1, 4 minus 4 is 0. This is going to be the exponents you normally have when you plug in these values. And when you plug these values in, here's what you're going to get. And there we go. And that's going to be your x and y values of this function. However, again, we are graphing the inverse of that function. So let's go ahead and just flip-flop our x and y's, or you can just graph them backwards, either way. And here's the x and y values you now have. And then as we graph those, we get a look at what our logarithm function would look like. Now let's go through and talk about all the things. And you do see your asymptote line there is now x equals negative 9. And again, you can see why. This value from your original function, you cannot take the log of a 0 or negative. So x plus 9 has to be greater than 0. When you move that over, you get a picture of where your asymptote line is going to be. Your domain values have to be from negative 9 to infinity. So you see that asymptote line there. Your range, however, again, is negative to positive infinity. Your end behavior, when does your graph go uphill? And that's to the left. As you approach that asymptote line. So as x approaches negative 9, you go to positive infinity. As x goes to the right, you decrease and you go down to negative infinity. Your x-intercept, again, we can't see it here. However, we could set our y value equal to 0 and we can solve it. Or think about it like this. You could take your inverse function and you could set your x value equal to 0, which is the same thing as setting your y value equal to 0 here. So let's take a look at that and see if we were to set x equal to 0 here, what would we get? And there you go. Setting, not the graph that we graphed, but setting our x value equals 0 in our inverse gave me the 0.07. So therefore, our graph, which is the inverse of that, would have the point on it, which is 7, 0. Okay, next problem. And I believe this is the last one. Again, you can solve this using your calculator and regular logarithms, or we can just find the inverse and graph, switch our x and y table. So let me go ahead and find the inverse here. And there is your inverse. Let's make a t-table for our inverse. And I'll show you again a little bit quicker way we can graph it on this one. So I'm going to plug in some values that's going to give me some negatives as well as positives. So maybe negative 1, 0, 1, 2, and 3. As we plug them in, here's the y values that we get. Okay, and there you go. And instead of recopying those down, if you just want to, in your mind, reverse your x and y's and plot those points instead. So instead of plotting the point -1, 2, 1, and 1/25th, plot the point 2 and 1/25th, comma, -1. Just flip-flop them as you're plotting them. The next point would be 2 and 1/5, comma, 0, which is right in there. The next point would be a 3, 1. Instead of 1, 3, the next point would be a 7, 2, 8, 9, I believe that's right. And the next point would be a 27, 3. So instead of actually having to rewrite all those again, if you just want to flip-flop them in your head as you're graphing them, you could do that as well. So there's my graph, my domain. Notice that your asymptote line is now here at 2, so therefore my domain is 2 to infinity. And as I said, with an asymptote line at x equals 2. Your range extends forever in both directions. In behavior, your function goes to positive infinity as you move to the right. Your function goes down to negative infinity as you approach your asymptote line of 2. You do have an x-intercept, which is located right here. And we can actually look at our points here. Since 0, 2 and 1/5 is on our inverse, then that means that our x-intercept would be the inverse of that, which is 2 and 1/5, 0, which again is located right there on our graph.